Welcome to another lecture, Formation of Solar System. The solar system's story is one of a transformation, how dust and gas floating through space combine to form the sun and its family of planets, moons and minor bodies. This process, spanning over 4.6 billion years, drives not only the motion of worlds but also the conditions that allow for life. So, in this lecture, we will be looking about early theories about the origin of solar system or universe, you can call it, formation of sun, components of solar system, and about the Goldilocks zone. So, early theories about the origin of universe. Nebular Hypothesis. It was proposed by Immanuel Kant and refined by Pierre Simon Laplace in 18th century. This theory posits that the solar system formed from a gigantic spinning nebula or cloud of gas and dust. Under gravity, the nebula contracted, spun faster, and flattened into a disk. Most material accumulated centrally to form the sun, while smaller clumps in the disk eventually became planets. However, this theory particularly accounted for planets' revolution in the same direction and plane, but it did not explain how dust became large planetesimals. Next theory is planetesimal hypothesis. It was proposed by Chamberlain and Moulton in 1905 and suggests that a near collision between the sun and another star drew out material from the sun, which cooled to form solid planetesimals that collided and merged into planet. It emphasized rocky planet formation and origins of asteroid, but it limited the limitations were it requires an exceedingly rare stellar encounter and does not match today's planetary arrangements. Coming up next is the gaseous tidal theory. By Jeans and Jeffries, this model involves the tidal forces during a close stellar pass, pulling streams of gas from the sun, which later became planets. It showed how gravitational explanation for drawing out potential planet forming material. However, the close passes are unlikely, and the theory does not explain orbital regularity or why matter would not disperse. Next is protoplanet hypothesis. Addressing the limitations of earlier models, positing that planets first formed as clusters or protoplanets which grew via collisions of smaller bodies, explains the variation in planetary sizes, origin of asteroid belts, and late impacts such as the late heavy bombardment. However, this theory was limited because of the precise mechanisms of initial dust to protoplanet formation remain incompletely explained. So, now hope you guys understood the early theories of origin of universe. Now let's look into about the formation of sun. Timeline and origin. Roughly 4.6 billion years ago, our sun formed a dense region of molecular cloud called the solar nebula. Triggered perhaps by a supernova, gravitational pull caused pulled the gas and dust inward, rising the central temperatures. Protosun and nuclear fission. When the central heat and density became extreme, the nuclear fusion began in the core, converting hydrogen to helium, which marked the sun's true birth. Protoplanetary disk formation. Excess material did not join the sun, but instead flattened into a disk, the nursery for planets, moons, asteroids, and comets. Sun's structure, core, which where the fusion happens, radioactive and convective zones where the energy transports happen. Photosphere is a visible surface where around the temperature is approximately 6000 degrees Celsius. Chromosphere and corona or the outer layers or the site of eruptions and solar wind. The sun spins differentially. Equator rotates faster than the poles, generating tangled magnetic fields. These fuel sunspots, flares, and drive the 11-year solar cycle. Sun's energetic outbursts influence the Earth's magnetosphere and climate as well. Now, looking into the components of solar system, let's look into the planets. The inner terrestrial planets. Closest to the Sun, Mercury, which is even smaller in diameter than some moons. Rocky, heavily cratered surface, lacks atmosphere, leading to massive temperature extremes. That is sometime minus 173 degrees Celsius to 427 degrees Celsius during the day, and it doesn't have any moons. Venus, second planet, similar size and mass to Earth, it can also be called as Earth's twin, but blanketed with a dense CO2 atmosphere and sulfuric acid clouds. Hottest planet due to runaway greenhouse effect. Surface pressure is 92% more than Earth's surface. Features include volcanoes and highlands. It rotates retrograde, that is, a day is longer than a year and has no moons as well. Earth comes third from the Sun. Uniquely supports the liquid water and an oxygen rich atmosphere. 70% covered in water, active geology, single large moon, and single magnetic field. Life on Earth has shaped and stabilized the atmospheric conditions. Mars, fourth planet. Reddish color from the iron oxide, home to largest volcano, Olympus Mons, and canyons such as valles marinaries. It has thin atmosphere, thin CO2 orbit atmosphere that is approximately around just 1% of Earth's pressure, polar ice caps, two small moons which are Phobos and Deimos. However, there is evidence for past liquid water and ongoing surface changes seasons due to similar axial tilt as Earth. The outer Jovian and ice giant planets. Jupiter, largest planet, more massive than all others combined. Its atmosphere is mostly hydrogen and helium with storms. That great red spot is the storm, and it has faint rings around it. There are more than 60 moons, including the four big Galilean moons, Io, Europa, Ganymede, and Callisto, which are mini worlds in themselves. It has strongest magnetic field among the planets. Moving on with Saturn, that's famous for its bright, extensive rings, ice, rock, dust. Second largest hydrogen helium atmosphere with more than 80 moons. Largest is Titan, which has a dense nitrogen rich atmosphere. Uranus, moving on to the next, is an ice giant, blue green color due to methane in its atmosphere. Extreme tilt, spins on its side, faint rings, has over 25 moons and has unique and complex magnetic field. The farthest known planet is Neptune, with the deep blue color, storms, and the strongest winds in the solar system. Several faint rings, and at least it has 16 moons. Largest is Triton, which is geologically active with geysers. Now let us look into the formation of moon. The most accepted theory is the collision of early Earth with the Mars-sized body Theia, that's around 4.5 million years ago. The impact ejected the material that formed a debris disk accreting the moon to the moon. So lunar rocks chemical similarity is found in Earth's crust as well. Simulations match current orbits. The axis stability keeps Earth tilt 23.5 degrees stable, supporting climate and seasons. Gravitational pull rises the ocean sides, which is crucial for marine life, affects Earth's rotation. Days are getting longer due to the tidal slowing. Plays a role in shielding atmosphere or shielding Earth from impacts and shapes the biology and culture as well. Now let's look into some other components. Asteroids, rocky remnants mostly found between Mars and Jupiter. It ranges from meters to hundreds of kilometers in diameter, irregular shape, and sometimes have small moons as well, and are leftover building blocks from the solar system's formation. Meteorites or small fragments, usually from asteroids or comets. Meteors or the streak of light seen as meteorites burn up entering the atmosphere. We can call it the shooting star which we see in the night sky. Next one is the meteorites. Those are the pieces that survey the atmosphere and land on Earth, giving direct evidence of early solar material. Comets. They are the icy bodies from the Kuiper belt and Oort cloud. Like they develop bright tiles as they approach the sun and their ices sublimate. Famous comets include Halley's Comet and Neowise Comet. Now let's look into Goldilocks zone. The Goldilocks zone refers to the region around a star where conditions are just right, not too hot or not too cold for liquid water to exist on a planet's surface, making it a prime target in search of for life beyond Earth. The term draws on Goldilocks fairy tale, which means optimal conditions for habitability. Now let's look into one PYQ from 2015. The term Goldilocks zone is often seen in use in the context of we just looked into what's Goldilocks zone. The answer is option C, search for Earth-like planets in outer space. This concept is foundational in astronomy, astrobiology, and planetary sciences for assessing other worlds' potential for life. The saga of our solar system's formation is a blending of cosmic processes, star birth, planetary assembly, chaotic collisions, and the emergence of life friendly conditions. By tracing current scientific understanding, we see how Earth and its neighbor are special products of universal laws and why their story is vital for all science. Thank you for joining this journey through the solar system. Keep exploring the stars. Do subscribe to the channel for more captivating journeys through space and geography. Thank you.